Okay, so last time we were talking about vibrational spectra and harmonic oscillators, and this time I want to move the conversation on and talk more about more advanced ways of thinking about vibrations, and also just very briefly sort of prelude next year's course and think about why we are getting what's called this fine structure. In other words, these very, very detailed transitions being shown in this infrared spectrum. So we had talked about the harmonic oscillator. So we talked about compression or release of the spring and how that increases the potential energy in the potential energy well once the spring length or the bond length in the case of a diatomic molecule deviates from an equilibrium value. Last time we called this spectroscopic transition. Here I'm just going to use the term the oscillation frequency. It's essentially the same thing, okay? And this bar here emphasizes that it's in wave numbers. So we define that oscillation frequency, spectroscopic transition, whatever you want to call it, as 1 over 2 pi c times the square root of the force constant, the sense of strength of the bond, divided by the produced mass, the heaviness of the atoms. So the heavier the atoms, the slower the vibration. The stronger the bond, the faster that spring is going to kind of come back in. Right, so we also then said that the energies of vibrational states are equal to v plus a half times this oscillation frequency. And again, we just used the term mu the last time, mu bar, but I just want to introduce this oscillation frequency term now because we'll be building on this in this lecture. So the gross selection rule for polyatomics. So we said that delta V can be plus or minus 1 for diatomic, but actually in more general terms it can be plus or minus 1, plus or minus 2, and so on. But we tend to see almost all transitions coming from the V is equal to 0 state, because Boltzmann said that's the most populated state. So therefore the transition that we see in a spectrum corresponds to the difference between 0 and 1. Even if it corresponds between 1 and 2 or 2 and 3 in a harmonic case, all of those values are the same. So how do we move this on a little bit? Well, the problem is that the harmonic oscillator is a pretty poor description of vibrations. Instead we use an anharmonic oscillator. In other words, it's not harmonic. So you see here the red curve is the parabolic curve of the harmonic oscillator. And instead we have this green curve, which is a better map of the potential energy changes as molecules, especially as the atoms in a diatomic are being pulled apart. So you can see the anharmonic oscillator. It's a pretty good map onto the harmonic oscillator as we compress the bond length, but as we lengthen it, you see it's a very poor approximation. And what this means, this has a couple of implications. The first is we still see this 0-point energy. Okay, so this lowest V is equal to 0 here is still non-zero. But as we increase in energy, because the well is widened, the steps up in energy levels get slightly less and less each time. So the green lines of the vibrational states here are slightly lower than the red lines of the harmonic oscillator. And this has to be the case because we must reach a stage where the molecule vibrates so much that the bond breaks. The atoms don't come back in again. So we must have some energy where we just completely release all potential energy in the system because there is no potential energy left because the bond doesn't exist anymore. And that's called the bond dissociation energy. So the extent to which the molecule will actually break, in other words, the strength of the bond, is given by this bond dissociation energy, the difference between the 0-point energy and the point at which the potential energy plateaus off to 0. Alright, so we see in anharmonic systems the molecule, the vibration levels are slightly lower. They're reduced by what's called an anharmonicity constant, and we'll come across that in a moment. So real energy levels are not equally spaced. So if we go back to our model previously, we can't just say that all the individual transitions are equally spaced, and we will reach a point where the molecule no longer exists. The bond will have vibrated so much that the two ends will disappear, and there won't be any attractive force to hold them back again. All right. So what does this mean then in terms of what we're talking about? We had said that for an harmonic oscillator, the energy of a vibrational state was V plus a half times the oscillation frequency. Okay. Now here we're just going to change that term slightly and call it the equilibrium oscillation frequency, just to be a little bit more correct. Okay, so this is why I'm changing to this sign omega, O-M-E-G-A, omega bar. That just tells us this is the equilibrium oscillation frequency. In other words, the oscillation frequency at the point at which the bond length is at equilibrium bond length. But taken away from this classical model, we need to account now for some anharmonicity. We need to say that, well, actually, as we go up the potential energy well, these levels are decreasing in energy a little bit. How much are they decreasing by? They're decreasing by this amount. V plus a half squared times omega bar E times some constant. This XE here is a constant, as we'll see in a second. And this is essentially the extent to which the width of the well, the extent to which anharmonicity is kicking in. And there's actually further terms in here, so this is actually an expansion. So there's a cube term, a quadratic term, a cubic term, and so on. So, but we just include the first term here because that's the only one that will be significant. All right, so we are accounting for anharmonicity. We are mapping this green curve here and using that to quantify energy vibrational states by adding in this correction factor. Again, we still have the 0 point energy, but now this is slightly different. It's not just a half times the oscillation frequency now, it's a half times the oscillation frequency upon 1 minus a half times the anharmonicity constant. So this is a slight correction. Usually it's a very, very small deviation from the actual 0 point energy in classical terms. Okay, the second thing we want to add into all of this is that, of course, if the selection rule for real molecules now actually is plus or minus 1, plus or minus 2, and so on, well, actually there are transitions, more transitions are possible than just individual 0 to 1, 1 to 2, and so on. So we can have 0 to 1, 0 to 2, 0 to 3, and so on, but also 1 to 2, 1 to 3, and 1 to 4. Now remember, we said almost all molecules exist in the V is equal to 0 state. So we'll just work on that assumption for the moment, but we'll come back to that in a little while. So there's a lot to take in here. We need to start pulling all this together. All right? So the first thing is we can make this simplification. So in rotational spectroscopy, we said because they're so close together in energy, in thermal terms, population of upper states is significant. However, as we saw in the calculation in the last lecture, population of V is equal to 1 state is tiny compared to V is equal to 0. So therefore, we can usually assume that all transitions come from V is equal to 0, but we're going to challenge that assumption in a while. So normally, we can say that transitions we see in infrared spectra are usually from V is equal to 0. So how do we work on calculating these transitions? So let me just move that out of the way here. Oops. What's the rogue? So I've derived these expressions, and you can have a look at that video. But essentially, what we're doing is we're taking the energy of the, say, first vibrational state. All right, so if I go here, and I'll switch to the dot-com in a moment, but I'm just going to write this equation out again on the dot-com. I'll have it on screen. So V plus a half upon omega bar E minus V plus a half squared omega bar E XE. Let me just switch to the dot-com for a moment now. So we can say, in vibrational spectroscopy, we can say the V is equal to 0, V is equal to 1 transition, okay, which is what we want to know in spectroscopic terms, will be equal to, well, E0 is equal to a half omega bar E, okay, so V is equal to 0, minus, that'll all be minus a half squared minus a quarter omega bar E xe, and E1 is equal to 3 over 2 omega bar E minus 1.5, so that'll be 9 over 4 times omega bar E xe. So this transition will be this first value subtracted from the second value. That means delta E transition, or what we might call the spectroscopic transition, is equal to omega E minus 9 over 4 minus 1 over 4 is 8 over 4, so it's 2 omega bar E xe, or we can back that out, 1 minus 2 xe. So that first spectroscopic transition, you can see here I've derived pretty easily, is omega E upon 1 minus 2 xe. So that's where these values are coming from in this table. The 0 to 1 is the difference. The spectroscopic transition here is omega bar E upon 1 minus 2 xe. This is the essential transition of importance in infrared spectroscopy. Why? Because Boltzmann says pretty much every molecule is in the V=0 state. So that means this is going to be the highest intensity transition we see, because it's the most probable transition. Almost all molecules will be in the V=0 state, so therefore any transitions that come from that state will be highly probable. And it's called the fundamental absorption. That V=0 to V=1 transition is called the fundamental absorption. We can also have a second transition, V=0 to V=2. All right, so delta V is equal to 2. Well, then this second transition here, so we have V is equal to 0 to 1, that's the first fundamental absorption. V is equal to 0 to V is equal to 2, that's called the first overtone, and of course V is equal to 0 to V is equal to 3. So we can very easily calculate expressions for those energy differences. This is the first overtone and the second overtone. And what you can see is, from the classical model, it's essentially the oscillation frequency, twice the oscillation frequency, 3 times the oscillation frequency, and then minus a small correction factor, depending on the extent to which the energy levels have been reduced in the anharmonic model. All right, so a good way of remembering is this is 1, 2, 3, 2, 3, 4. Right, so the next slide here, I've essentially derived those. That's the equation I did on the DocCam. So we see here, to derive the fundamental absorption, it's essentially taking away E0 from E1 and factorizing that, or for the first overtone, E2 from E2 minus E0, and you see we get that expression there. So that's all derived in full detail if you want to have a look at that on the YouTube link. What does this mean? Well, this means we can actually start to get quite a lot of very detailed information about the anharmonic oscillator. Because normally when you run an infrared spectrum, you run it from, let's say, 500 to 4,000 wave numbers. So if I run this spectrum from 500 to 4,000 wave numbers, and the fundamental absorption we saw for HCl is about 2,900 or so, 2886 wave numbers. So that means I'm going to see a peak for HCl here. And it's a very detailed spectrum here. We'll explain that in a while. But essentially, we see this peak for HCl. Now, just note that this axis here is normally in reverse. Okay, so if you're used to looking at infrared spectra, you'll normally see, for example, 4,000 on the left-hand side and 500 wave numbers on the right-hand side. Here it's going in increasing order. This is just slightly different. But we're also saying, if you go back to our model, we're also saying, okay, so that 0 to 1 is 2,900 or so wave numbers. But we're also saying a 0 to 2 transition is possible. And that 0 to 2 transition, we can just about see it here. Now, we know it's going to be about double the value. All right, we know it's going to be about twice the fundamental absorption. So when we're hunting for this, and you'll do this in your third year labs, when we're hunting for this in the spectrum, we go to about double the fundamental, and we can see here tiny value. Why is it tiny? Well, remember, vibrational states are mapped by wave functions, and the probability of a transition will depend on how well those wave functions interact with each other. So they interact very strongly for the 0 to 1 transition, but not nearly as strongly for the 0 to 2 transition. So that's why the first overtone is much weaker. Of course, if this is a harmonic system, this value will be exactly double this value. Okay, so if this was a harmonic system, well then twice the 2886, we should see this peak at 5772 wave numbers, but we don't. Okay, so the fact that we're seeing this slight decrease in the value of the first overtone is proof that we have an anharmonic oscillator. And that means then we get data for our equations. Alright, we've got two pieces of information now. We know the energy, the transition for the fundamental absorption. We know the energy of the transition of the first overtone. So that allows us now to use these numbers to get information about the anharmonicity constant and the equilibrium frequency. We're able to get much more specific detail about the equilibrium oscillation frequency. Okay, so let's have a go at doing something like that. So we know from our expressions that delta E for the fundamental absorption is equal to omega E upon 1 minus 2xe. And we know that the the transition energy of the first overtone is equal to 2 times omega bar E upon 1 minus 3xe. So here we're told the fundamental absorption, 2886, the weaker one, 5668. Okay, so here are two peaks that we see, 2886, 5668, and actually it's giving us the data for the third one, the 0 to 3 transition, second overtone, 8347. Alright, so if we were to have a very, very sensitive spectrometer and went up to about 8,000, we would see a tiny little set of peaks here corresponding to the HCl second overtone. So how do we use this data? Well, that means that we know that this value here is equal to 2886. This value here is equal to 5668. So that means we can use simultaneous equations to work out we have two pieces of information and we have two unknowns, so we can use simultaneous equations to work out the value of omega E and the value of the anharmonicity constant. So if I take equation, let's say this is equation 1, this is equation 2. So if I take equation 1 and multiply it by, let's have a look and see what I've done here. So equation 1 multiplied by 2. That means I get 2 times delta E is equal to 2 omega E, 3 omega E on 1 minus 2 xe is equal to 3 times this, which gives me 8658. And if I take equation 2 and multiply it by two. Let's have a check here, see what I've done. We want to obviously isolate the, so here I've got 2xe. Oh yeah, so that'll give me 6, so I need to multiply this one by 2. Give me 6. So 2 times delta E is equal to 4 omega bar E on 1 minus 3xe. Okay, so 3 times, oh, I'm sorry, yeah, we don't need to multiply that at all. So, sorry, let's start it again. So we've got 1 times 3, so that means 3 omega bar E upon 1 minus 2xe is equal to 8658. And I'll leave 2 as it is. 2 omega E upon 1 minus 3xe is equal to 5668. What we're looking for here is this 3 times 2xe will give me 6xe. This 2 times 3xe will give me 6xe. So when I subtract both of those equations, you end up with just an expression in omega E. Right, because the xe omega E cancel will be equal to 2990 Redmond. So the equilibrium oscillation frequency of HCl is 2990. Okay, so we can't get that directly from the spectrum because the spectrum value itself is distorted by the anharmonicity constant. So this is giving us the actual value of the HCl vibration, not worrying about anharmonicity. And then once we have this omega E value, we're able to sub it back in. So I can say, for example, 2886 is equal to 2990 on 1 minus 2xe. I use equation 1. And that means I get xe of about 0.0174. We don't have any units there. So this 0.0174 is a measure of the effect of anharmonicity. So that's a multiplying effect detracting away from the energies of the vibrational states. Alright, so we can see how easily data from experimental information is able to give us a way into working out the equilibrium oscillation frequency before we have to account for anharmonicity. Then it's asking us to calculate the force constant of the bond. Well, that's easy now because now we have this equilibrium oscillation frequency. We can say that that's equal to 1 over 2 pi c times square root of k over mu. So that means k is equal to 4 pi squared c squared omega bar e mu. Okay, so getting rid of the square root and multiplying across. So when we shove everything in, we get k is equal to 516. If you were to work the units out, you'd actually get kilograms per second squared, but that actually works out to be Newton per meter because 1 Newton is equal to 1 kilogram meter per second squared. Okay, so we quantify force constants in newtons per meter. Alright, so this is giving us again structural information about the strength of the HCl bond. Okay, so if you want to go through that in more organized detail, a video link will be available. So I mentioned, sorry again, that's just disappeared off the screen. I mentioned that about, or a small fraction of molecules won't be in the V is equal to 0 state. They'll be in the V is equal to 1 state. And this really depends on the temperature. So actually, we may find that we have transitions not only from V is equal to 0 to V is equal to 1, but transitions from V is equal to 1 upwards. All right, and really the only one of importance here, because of this wave function overlap issue I mentioned earlier, is the V is equal to 1 to V is equal to 2 transition. And this is called a hot band, because essentially it is caused by the temperature of the system being high enough to allow it to be seen. And if we were to do the same trick of subtracting, for example, the V is equal to 2 energy level, taking away the V is equal to 1 energy level, what we find here is we get an omega E value, again, difference between 2 adjacent states, times some correction factor due to anharmonicity. Alright, so we see a slightly smaller value than the fundamental absorption. So sometimes what you see in spectra are a peak Okay, so if you're just looking at an infrared spectrum, sometimes when you see a spectrum, you may see a slightly lower energy value just off to one side. So you might see a slight little deviation here, and that can be due to the hot band. Okay, so let me just... So the last thing is just to mention, and again, I'm not going to go into this in detail, but the spectrum I'm showing you isn't the normal infrared spectrum that you've seen. Okay, so this is actually a spectrum of cigarette smoke, and again, it's an experiment that many of you will do in third year. And this isn't your typical infrared spectrum. We're used to seeing sort of quite broad bands or sharp spikes or whatever. And the reason is it depends on the resolution of the spectrometer. So if we have a spectrometer that is able to detect at very, very fine detail differences in energies, well then we can observe spectra that look something like here. So this idea of low resolution or high resolution, this is essentially how good is the instrument, how fine in detail is the instrument capturing the information that's being sent to it. So here we see we get these broad, featureless bands about 3000, but actually if we were to use a very high resolution instrument and zoom in about 3000, we see that each of these broad bands is actually, this first peak here is actually this set of peaks, and this second peak here is actually this set of peaks. So we actually see there's a lot of what we call fine structure in that. What is that fine structure reminding you of? Hopefully you're all shouting it from your laptops. Rotational spectroscopy. You see here we're seeing the increase in equally spaced peaks and followed by a decrease again associated with that peak. And again here, increase in intensity up to a maximum followed by a decrease associated with that peak. Okay, so this vibrational infrared spectrum giving us vibrational information, actually underneath it all is a whole load of rotational information. And we shouldn't be surprised because we said in rotational spectroscopy we were looking at rotational transitions within a particular vibrational level. So each vibrational level has its own set of rotations. So we're not going to talk about this in too much detail, but it's just important to note that when we look in spectra generally, and we'll see this again when we look at UV visible spectra, when we tend to see these sort of broad, featureless bands, quite a lot of stuff is happening underneath here. All right, what's happening underneath? Well, if we think about a vibrational transition, we've just been talking generally about V is equal to 0 going to V is equal to 1, that fundamental absorption. But of course the V is equal to 0 itself has a set of rotational states, and the V is equal to 1 has a set of rotational states. So the actual decision for a state to move from one state to another, there's a whole load of possibilities, and they all differ in very small amounts of energy by 2B, because of rotational spectroscopy. So that we will see that instead of just seeing one transition for vibrational spectroscopy, they tend to be a little bit broader. And the reason they're broader, the reason we don't see a spike like we saw in rotational spectroscopy is because underneath that that broad peak is a lot of fine structure associated with the rotational transitions. Okay, now that's the limit of detail we'll go into this year's course, but next year you'll have a look at really working out in quite a lot of detail how we're able to calculate the energy of those transitions and really give a lot of information about what's called the rho-vib spectrum, in other words, rotational vibrational spectrum. It's quite a nice analysis. All right, so I think we'll leave vibration spectroscopy there. Essentially, the two parts of it are looking at harmonic oscillators and then moving on to anharmonic oscillators. And in anharmonic, then we teased out this idea of comparing fundamental absorption in first and second overtone, and then just introduce the idea of the hot band. And a lot of these concepts are really just to set the scene for what you'll pick up in third year. The core principle here in our course is a spectroscopic transition is the difference between two energy levels. Okay, so you just need to go to sleep at night saying that mantra. A spectroscopic transition is the difference between two energy levels. And once we know what those energy levels are, and once we're able to account for the values of those energy levels, we're able to very easily then work out the energies of transitions. That's what we see in our spectrum, and that's what we're able to use then to probe the structure of the molecule. Okay, so the next time we'll move on to the last part of the series of transitions. All right, so if you go to our course overview here, we've looked at rotational transitions, we've looked at vibrational transitions. Next time we go the whole jump, we leave an electronic state altogether and move right up into the next electronic state in what are called electronic transitions or UV-Vis spectroscopy. So I'll pick that up in the next lecture.